These are the solutions to calculus homework number 21. So it first starts with 6 problems from the textbook before a handout. So starting with number 17. This text is cut off, but it says give a possible formula for the function that is graphed right here. So we have several different points of interest. The first is we know that this is a y of t function, and it does appear to be exponential. So we are going to assume that it is an exponential equation of the form y of t equals y naught times some base raised to the t power. So for this particular situation, we know that y naught is the intercept here, which is 500. That's our initial value of y. And then we know that y of 3 is equal to 2,000. So we can just go ahead and say that the 2,000 is equal to 500 times a raised to the t. So solving for this, we want to figure out what a is. So this is a little tricky. So we have both sides divide by 500. And so what we have is 4 equals a raised to the t. I'm sorry, this should actually be a cubed, as we are doing y to the 3. And so now we want to take the cube root of both sides. So this will give us the cube root of 4, which is not a very pretty number. But if you go into your calculator and you find the cube root of 4, you find that it should be 1.5874. So that's our base. So the possible formula for this is going to be y of t equals 500 times 1.5874 raised to the t. So in number 19, we have a population growth. So we want to calculate, or not really calculate, but come up with a function that describes population of the world based on this information. So we have a couple different things that we can pull from this. So let's say that our initial population is 4.453. So P0 is 4.453, and that's billion of people. And so to write to see where this is going, so we have population as a function of time will be P naught times a raised to the t. So we know that we can set t as years since 1980. And by doing that, we can say that P in 1998, which is 18 years after 1980, will be equal to 4.453. Actually, sorry, we should say it like this. Will be equal to the 5.937, which is also equal to the 4.453 times some factor raised to the 18th power. So we'll divide both sides by 4.453, and we will end up with 1.333 approximately, which is equal to our base raised to the 18th power. And then we just take the 18th root of 1.333 and the a to the 18th. So this is a little weird, but just in case you've forgotten, in your calculator you can type 1.33 or whatever raised to the 1 over 18th power. And this will give us the same as an 18th root. So this gives us a base of 1.01611, which is equal to a. And so our function actually ends up being P of t equals 4.453 times 1.01611 raised to the t. And t is still years since 1980. So in order to predict the population in 2008, we'll say that t is 28 because that is the number of years since 1980. So we'll have P of 28 equals 4.453 times 1.01611 raised to the 28th power. So plugging this into your calculator, you should get a population of about 6.966 billion people. And to compare that to our 6.771, it's a little high. So we'll just say that this is slightly higher than the actual, because all we want is a comparison of the two. Number 26 asks, could this data on annual world soybean production correspond to a linear or an exponential function? If so, which? So to do this, I'm just going to take a look at how the production changes from year to year. So if I look from production year 1 to year 2, I see that what's actually occurring is our change in production would be 170 minus 161, which is 9.3. And then for the next one, it would be 180.2 minus 170.3, which is 9.9. Then we have from 190.7 minus 180.2, which is actually 10.5. And then from this to the next, we actually have 11.1 is the change. And for the last one, we have 11.7. So it does not appear to be linear based off of the change. Otherwise, we would see that delta P is constant per year. Therefore, for part A, we will say that this could be exponential. Now B says, find a formula for P, which gives the world soybean production in millions of tons as a function of time in years since 2000. So the form we'll have is P of T equals P initial times A raised to the T. So we just need to figure out this factor. In order to do that, we're just going to look at the relative or percentage rate of change from one year to the next and assume that it's going to be constant if this is an exponential function. So for the first 2 years, we would have 170.3 minus 161.0 over 161.0. So this will give us our rate of change. So when we put this into a calculator, we actually get an R value of 0.057764, and that's our R. Therefore, since A is 1 plus R, our base is going to be 1.0577764. So our function should be P of T equals our initial, which is 161, times 1.0577764, I'm not going to round it at all, raised to the T. And there's our production function. And so the annual percent increase is just taking our R and multiplying by 1,000. So we have R, I'm sorry, not times 1,000, times 100. So our R is just going to be 0.057764, so our percentage is going to be 5.7764% per year. So this question is about inflation. So using the following information, we want to decide if minimum wage has kept pace with inflation. So looking at the minimum wage, we're going to see if it has grown by 4.3% per year. So in order to do this, we'll say wage as a function of time. It's going to be our initial wage times some base raised to the T. So our initial is going to be 25 cents, so we'll say $0.25. And we know that after some number of years, we have a wage of $5.15. So we need to know how many years have passed since 1938. So we have 2004 minus 1938, which means that our T in this case, which is years since 1938, is actually going to be 66. So T would be equal to 66 for this data point. So what we have is W of 66, which is equal to $5.15, is going to be equal to 0.25 times some A raised to the 66th power. So, dividing both sides by 0.25, we have the equation 20.6 equals A raised to the 66th power. So we're just going to take both sides and raise them to the 1/66th power, which is how to get rid of this 66. And what we end up with is an A of 1.0469. Now, what information that gives us is, since A is equal to 1 plus R, we can say that R is actually A minus 1. Therefore, R is going to be 1.0469 minus 1, which is 0.0469, or in percentage, 4.69%. So, what does that tell us? That actually tells us that our minimum wage is increasing at a faster rate than inflation. Question 30 has to do with whooping cough. And it is now known that the vaccination wears off at some point. So, there's been an increase in number of cases, which is W, from 1248 in 1981 to 18,957 in 2004. So if T is years since 80, let's find an exponential function that fits this data. So our W, which is as a function of T, is going to be equal to our initial number of cases times some base raised to the T. So what information do we have? Well, we have that W of 1, because it's 1 year since 1980, is equal to 1248. We also know that W of, so years since 1980, W of 24, which would be the year 2004, is equal to 18,957. So, using this information, we need to come up with a function. So since W of 1 is equal to 1248, we can say that 1248 is equal to W0 times A, which is raised to the 1. So we also know that W of 24 is equal to 18,957. So we have 18,957, which is equal to W0 times A raised to the 24th power. So we actually have two unknowns and two equations, equation 1 and equation 2. So we can solve this as a system of equations. So one way we can do it is just to substitute. So let's go ahead and say that W0 is, using equation 1, 1248 divided by A. When we do that, we can substitute it in to equation 2, and this gives us that 18,957 is equal to 1248 over A times A raised to the 24th. So this lets us cancel out one of our A's, leaving us with A raised to the 23rd power. So the next step is solving for A. So we can divide both sides by 1248, so we have 18,957 divided by 1248 is equal to A raised to the 23rd power. So plugging this into our calculator, we have 18,957 divided by 1248, which is 15.1899, set equal to A to the 23rd. And we're just going to take both sides to the 1/23rd power to get rid of the 23rd power for A. And this gives us a value for A of 1.12557. So the last bit is we can go back into equation 1 and find W0. So how do we do that? Well, we say 1248 equals W0 times a to the first, which is 1.12557 raised to the 1. So simply just dividing both sides by this number, we end up with a W0 of 1108.77. So our equation works out to be 1108.77 times 1.12557 raised to the t power. Question B says, what does your answer to part A give as the average annual percent growth rate of the number of cases? So this just comes from A. So since A is equal to 1 plus R, R, which is our rate, is A minus 1. So we would have 1.12557 minus 1, so our rate is 0.12557. Or we can say that is 12.557% per year. Now C asks us that the number of cases had more than doubled between 2000 and 2004. Does our model confirm that report? Well, all we have to do is just check what it was in the year 2000. So we'd say W of 20, because that's the year since 1980, is equal to 1108.77 times 1.12557 raised to the 20th power. So plugging this into our calculator, we see that this is 11,811.2. So compared to the 18,957 it was in 2004, it does not double. From those years. So question 31 asks us, if an aircraft takes off at a different elevation, it needs a different amount of time or a different amount of distance to roll down the runway before taking off. So we want to determine a formula for this particular aircraft that gives the takeoff roll as an exponential function of airport elevation. So we want to say, so we'll say roll as a function of elevation is going to be equal to some initial value, we'll say is R0, times some base, which is A, raised to the E power. So we can do this a couple ways, but we can say that at sea level, where our elevation is 0, we can find our R0. So that means that at sea level, our takeoff roll is 670, sorry, that looks like a 6, 670 feet. Now, to get our next part, we can just use a later point. So it doesn't really matter which one you choose, but it makes a lot of sense to just do the 1,000 here. We will say that at E equals 1,000, R of E will be equal to 734. So, what does this give us? Well, R of 1,000 is equal to 670 times A raised to the 1,000th power. So, how do we go about solving this? Well, we know that that's equal to 734, so we will divide both sides by 670. And so A raised to the 1,000th power is 734 divided by 670, which is 1.09552. And so our A, which we can just raise both sides to the 1/1000th power, will give us Pardon, I did not input this correctly. A very strange but small a of 1.00009. Therefore, our function, which is roll as a function of elevation, is going to be 670 times 1.00009 raised to the e. For our handout, we're going to start by filling out this table. So first, to determine whether a function is increasing or decreasing, we simply look at the base that is raised to some power of t. If it's greater than 1, it's increasing. So here we have 4, which is greater than 1, so this is increasing. 5.5, increasing. 0.98, less than 1, so it's decreasing. 0.75, also decreasing. And 3, increasing. Now, by what percent comes from the fact that a is 1 plus the rate, or rate is a minus 1. Now, to get percent, of course, we would multiply by 100%. So here we would have 4 minus 1, which is 3 times 100, or 300%. Here, 5.5 minus 1 is 4.5 times 100 is 450%. For h, we would have negative 2%, or just a 2% decrease, since we already said. For p of t, 25% decrease. For L of t, 200% increase. Now the frequency is pretty easy for the first one, right? Every time we plug in one step for t, it goes by 300%. For g of t, however, in order to step by 450%, we would actually need to plug in a t of 10. So that would mean that we have 1/10 of a step per unit in order to get a 450% change. Same thing would go for h of t, which is 1/3 per unit. For p of t, it would be 3 times per unit. That means that every time I step t by 1, it goes 25% 3 times. Then for the last one, of course, 2 times per unit. Now for 2, we're just coming up with a function. So we have f of, we'll say f of x, and it will be our initial value, 35, times our value for a. So a is going to be 1 plus r. R in this case is 0.35, but it's decreasing, so it's negative. So a would be 0.65. And then it decreases at this rate every 5 units. So if you think about it, we need 5 units in order to have one decrease of 35%. So that means this actually needs to be 1/5 times x as our power. For number 3, so let's do g of x this time. We'll have initial value of 2.5. This time we're increasing at a rate of 6.5%. So that would be a equals 1 plus r. R is 0.065 if it's 65%. And it's positive because it's increasing. So we have 1.065 as our a. So it's 2.5 times 1.065, 5 times per unit. So I will have 5 times this should be x. For number 4, f of 5 is 27, and it decreases by a factor of 0.8 3 times per unit. So a is 0.8. And so what does this function look like? It'll be f of x equals some f naught times 0.8, and then it's 3 times per unit, so raised to the 3x. So since f of 5 equals 27, that would also be equal to f0 times 0.8 raised to the 3 times 5. So if we plug this into our calculator and solve for f0, 0.8 raised to the 15th power is 0.035. So I have 27 equals f0 times 0.035184. Then I just divide both sides by that odd number, and I get a very large number of 767.386. So my function is going to be f of x equals 767 0.386 times 0.8 raised to the 3x. For 5 through 7, we want to describe the functions with frequencies and percent change, making sure if it's increase or decrease. So, starting at 150, we have an a value that is less than 1, so it is going to be decrease. So a is going to be 0.5, and so r is a minus 1. So therefore, that's going to tell us that r is 0.5, or 50%. So we're going to be decreasing by 50%, decreasing by 50%, and then it's going to occur twice per unit, or 2 times per unit. For g, we're going to have an initial value of 23. We have an a that is larger than 1, so a is 5, therefore r is going to be 4, or 400%. So we're going to be increasing by 400% once per 5 units, because I would have to plug in a 5 in order to get 1 step of 400%. Then for h of x, we start at a value of 45. We have an a that is 1.25. Therefore, r is going to be 0.25, or an increase of 25%. So we're going to be increasing 25%, and we're going to do that once every 3 units.